Welcome to this comprehensive guide on multithreading and concurrency in C Sharp, essential concepts for building responsive and efficient applications. These techniques allow programs to perform multiple operations simultaneously, significantly improving performance and resource utilization. This is particularly useful for I/O bound work, complex calculations, and maintaining a responsive user interface. Let's start by defining some key concepts that form the foundation of multithreading. A thread is a single sequence of instructions within a process, acting as the smallest unit of execution. Multithreading involves multiple threads running concurrently within the same process, sharing memory and resources. Concurrency refers to a system's ability to handle multiple tasks over overlapping time intervals, whether truly simultaneous or interleaved. Parallelism, on the other hand, means tasks literally run at the same time, often on different CPU cores. Processes are independent program instances, each with its own memory space and system resources. Tasks represent asynchronous operations and are a higher-level abstraction over threads, offering easier and safer management. Now let's dive into implementing multithreading in C Sharp. The thread class is fundamental for creating and managing threads in C Sharp. You create an instance of the thread class, passing it a thread_start delegate that points to the method to be executed. Then, the start method initiates the execution of this new thread. The task parallel library, or TPL, provides a higher-level abstraction for multithreading, simplifying thread management. The async and await keywords are used to write asynchronous code that doesn't block the calling thread. When multiple threads access shared data, synchronization mechanisms are crucial to prevent race conditions. The lock keyword ensures that only one thread can access a shared resource at a time. The monitor class offers finer control over thread synchronization than lock, including signaling mechanisms. A mutex synchronizes threads across different processes, while a semaphore limits concurrent access to a resource. Interlock provides atomic operations for simple tasks like incrementing a counter, ensuring thread safety without locks. Let's explore C# async/await in more detail. The async keyword marks a method as asynchronous, allowing it to perform non-blocking operations. The await keyword, used within an async method, pauses execution until the awaited task completes, without blocking the calling thread. Asynchronous operations are represented by task and task T objects, which encapsulate the ongoing work. The C# compiler transforms code using async and await into a state machine to manage these operations efficiently. Now, let's consider multithreading specifically within Unity 3D. Unity is not inherently thread-safe, meaning direct manipulation of Unity objects from background threads is generally not allowed. The Unity job system provides a safe and efficient way to perform multithreading within the engine. Jobs are units of work that can be executed in parallel on worker threads, optimizing performance. The job system includes safety checks to prevent common issues like race conditions and data corruption. Communication between threads in Unity can use techniques like double buffering, but C# locks can block the main thread. Coroutines offer another way to manage multithreaded-like code in Unity, allowing operations to be spread across multiple frames. To ensure robust and efficient applications, follow these best practices. Avoid overusing threads. Creating too many can lead to significant overhead. Instead, use thread pools or tasks to manage concurrency efficiently. Use locks sparingly, as their overuse can create bottlenecks. Consider lock-free techniques like interlocked for simple operations to improve performance. Always prioritize thread safety to prevent race conditions and ensure data integrity. Thoroughly test for race conditions using unit tests and stress testing to identify and fix issues early. Profile your application to identify bottlenecks and optimize concurrency for peak performance. Choose appropriate techniques based on the operation type, parallelism for CPU-bound tasks, and async/await for I/O-bound tasks. CPU-bound operations require significant CPU resources for calculations, like image processing or data compression. I/O-bound operations spend more time waiting for input/output to complete, such as reading files or network requests. Let's look at an example scenario in Unity 3D, offloading terrain generation. Calculating complex algorithms like terrain generation can be too slow if run on the main thread, causing hitches. The solution is to offload this heavy computation to a background thread using the Unity job system or system, threading. First, create a job that implements the terrain generation algorithm. Use native arrays to efficiently pass data between the main thread and the job. Then, schedule the job to run on a worker thread, allowing it to execute in parallel. Once the job completes, copy the results back to the main thread and update the terrain. A coroutine can manage the thread and update the Unity scene progressively. Mastering multithreading and concurrency will significantly enhance your C# applications, making them faster and more responsive. Thank you for watching this guide. Keep exploring and building amazing things with C#.